In this video, we will take up a problem from design based on the concept of shear stress. Okay, so the problem goes like this. So there is a shaft like here, and then it is trying to transfer some power from this side to another shaft which is on this side, which basically may be connected to the load like a generator or something. Now, so how to connect these two shafts? So these are connected by a coupling like this, which is called a flange coupling. So this is a disc which is rigidly connected to this shaft, okay, maybe welded or something. And similarly, another disc is here, which is rigidly connected to this shaft. And then we bolt these two discs, okay, with several bolts or something. Okay, so in this case we have shown that there is a single circular way we have put the bolts, and the question so this circle is called the pitch circle, okay, and its diameter is 14 centimeters, okay, and there are number of bolts are 6, so we have 6 bolts on this pitch circle, and the power to be transmitted is given as 250 kilowatts. From this side to that side, the power transmission has to be 250 kilowatts maximum, and this power has to be transmitted at an angular speed of 1000 rpm, okay, and the material of the bolts, so here the bolts are inserted, and the material of the bolts has a allowable, sorry, this is not sigma, this is shear stress, okay, allowable shear stress of 75 Newton per millimeter square. Fine. So you have to calculate what should be the diameter of each of the bolt that you should put there. So that's why it's called a design problem. Okay. So you are basically designing the bolt. So what should be the diameter based on shear stress. Okay. Now, so how to think about the problem? See, you are thinking that there is something like a bolt. This is the bolt head, and so this is the part which gets inserted here, and once this side of the flange tries to rotate this, so there will be a section here, okay, which will be coinciding with this junction. So there the bolt would try to shear off, okay, as if this side will just be sheared off from the upper half. So that means, so this is the area which is now taking the total shear stress. Fine. Now let's say we assume that the diameter of the bolt which we are going to design is D. Okay. Now what is the maximum shear stress that can exist there? So this is the maximum one, right? So that means if tau max is the maximum shear stress times the area of one of the bolt, so one of the bolt is say pi d square over 4, so this is the force which is taken by one of the bolts. Fine. And then so and like that we have 6 such bolts are there. Fine. So that means so times 6, so that should be the total load which can be taken at this so in a way what we can do is, okay, anyways, So because here it is the torque which is getting transmitted, so and this is the load. Okay, so that means this force times this distance, right, this radius, which is I think 7 centimeters. So that is the torque which is resisted by each of the bolts. So similarly this will be another one, this will be another one, so like that. Fine. So 6 times this times the pitch circle radius, so radius pitch circle. Okay, so this is the torque basically. Fine. Now but then we do not know what is the torque that is coming, right? We are given only the power and the rpm. So let's now calculate. Okay, so this is the torque maximum, because this is maximum, so this is maximum. But then from the power side, how to calculate the torque? See, your power is nothing but the torque times the angular speed, right? So that means suppose torque is t times what is the angular velocity? So this is 1000 revolution per minute. So this is revolution per second, okay, times 2 pi. So this is the radians per second. Fine. And this power is given to be 250 into 10 raised to 3 kilowatts. Fine. So from here you can calculate T to be equal to if you calculate this, it will come out to be 2380 Newton meter. Fine. So this has to be equal to this. Fine. So all the other dimensions are given, rp is given, tau max is given, so only thing we have to calculate is this. So now, so 2380 should be equal to 75 Newton per millimeter square. Okay, so but then so then this also we should put in, one has to be careful about this, is in millimeter square. Fine. So that the dimensions, the units you have to be careful about. This is in Newton meters. Fine. Into pi. Now this d will come out in, if this you keep in millimeter square, so the answer also d will come out in millimeter square, so that you should be careful. Pi d square over 4 is the area of 1, then times 6 times so because this height is Newton meter, so this we have to convert into meter. It is 0.07 meters, half of this. So from here you can get diameter to be equal to 9.82 millimeter. But then generally because it's a design problem, you shouldn't say that it's 9.82, so at least D should be of 10 mm diameter. So that's how you should calculate. Okay, so that was an easy problem, but yeah, so you should think how to convert this power at a given rpm into the torque, and that torque is getting transferred by all the 6 bolts. So each bolt has a cross-sectional area which is responsible for taking this thing. So that's how you solve it. Okay, so we will see another problem in the next video. Thank you.